our today's problem from rigid dynamics. Okay, and the problem is a system of n particle moves under external force and their action and reaction. Okay, write down the equation of motion of ith particle and also find the motion of the center of mass. This is our problem. We have to find out or write down the equation of motion of the ith particle, and also we have to find out the equation of motion of center of mass. Before going to proof or going to discuss about this problem, we here discuss about an important principle of rigid dynamics, which is known as D'Alembert principle. And D'Alembert principle says that reverse effective force acting on each particle of a body together with external force act on it, that is act on this particle, are in equilibrium. Right? This is the D'Alembert principle. Now here we get an word, reverse effective force. What is reverse effective force? To understand reverse effective force, we first know what is effective force. Effective force. What is effective force? Let it be a particle of mass m and an acceleration or force act on is, this is F. Then the force mF or this force mF is said to be effective force on the particle. Okay. Now if we divide the acceleration F into three parts, that is along x-axis, y-axis and z-axis, then we know that F, this is a vector, this is x double dash I cap, y double dash or double dot j cap, z double dot k cap. Okay, so we say that mx double dot, my double dot and mz double dot are the effective force along x, y and z axis respectively. Right? And similarly, if we write m into d2s by dt2, we know that d2s by dt2 is the tangential acceleration. So this is tangential effective force or effective force along the tangent. And similarly, m v square by rho is the effective force along the normal. Okay. Now effective force with direction reverse is said to be reverse effective force. That is, we say that minus mx double dot is the reverse effective force along x-axis. Similarly, minus my double dot minus mz double dot and so minus m d2s by dt2 and minus m v square by rho. And we say that minus mf, this is the reverse effective force act on the body. Also, the external force, if capital F be the external force act on the body, this is capital F. Capital F is external force act on the body. This is also said to be impressed force. This term is also very important for this topic. Okay, and effective force we already discussed here is also known as kinetic reaction. Effective force is also known as kinetic reaction. Okay, so these are the impressed force, This is effective force, this is kinetic reaction also, and this is reverse effective force. Now we go our main topic. We first write down the equation of motion of the ith particle. Before writing the equation of motion of the ith particle, we let here a system of particle consisting n particle. Here it is given that n particle in the system present. Here we consider a system of particle consisting n particle. Let this be a system of particle consisting n particle. Let it be R1, it be R2, it be R3, and so on, it be Rn. Okay, this is the system of particle. And mass of each particle, the mass of this particle is M1, mass of this particle is M2, and this is M3, and so on, this is Mn. Right? Let here the ith particle is at Pi. This is the ith particle, and position vector of ith particle is Ri, and the mass is Mi. Okay, and let the origin is at O. So it is clear that O and Pi, if we draw O and Pi line, then this is Ri, this is the position vector of ith particle Pi. Okay. Now let external force act on ith particle is Fi. Okay. Here we write let Fi be the external force act on ith particle. Particle whose position vector is Ri and mass is Mi. For I, this is equal to 1 to n, because the system consists n particle, right? And let Rij, capital Rij, be the internal force act on ith particle by the jth particles. Okay, we know that there is always a action and reaction to every particle to each other. Okay, and since the system consists in particle, here we let Rij be the internal force acting on the ith particle by all the jth particles. Okay, so the total internal force, on ith particle is given by summation j, this is equal to 1 to n Rij. Okay, and we say that on the ith particle there be an external force which is Fi, and there be another internal force which is given by summation j equal to 1 to n Rij. Okay, and we know that acceleration of the ith particle by the external force is given by acceleration of ith particle is given by Ri vector double dot. We differentiate Ri vector with respect to t two times. Okay, it is denoted by Ri vector double dot. So we write the equation of motion of the ith particle as, here we write Mi Ri vector double dot. This is mass and this is acceleration. So this is Ma. Okay, this is Ma, and the total force on the ith particle is given by Fi plus summation. The internal force is summation J. This is equal to 1 to N Rij. Okay, and this equation is the equation of motion of the ith particle. Right, here the external force we may give here and vector sign because this is also a force, and this is the equation of motion of the ith particle. That is the answer of the first part of our problem. Okay, we name this is relation number 1. Now if we take summation over I equal to 1 to n, then we get summation Mi Ri vector double dot summation I, this is equal to 1 to n. This is given by summation Fi I equal to 1 to n plus this is summation I equal to 1 to n, and here already j equal to 1 to n present Rij. We may give here also a vector sign. Okay. Now we know that for a system of particle or for any body, internal action and reaction or sum of internal action and reaction is equal to 0. So this term must be vanish. Okay. So here we write, since double summation I equal to 1 to n and j this is equal to 1 to n, this is I, Rij this is equal to 0. Since internal action and reaction on a system of particle is always 0, so we get the result as this is summation I equal to 1 to n Mi Ri vector double dot, this is equal to summation I equal to 1 to n, this is Fi. This relation can also be written as we write in the form summation I, this is equal to 1 to n Fi, this is the external force, plus this is minus summation I equal to 1 to n Mi Ri vector double dot, this is equal to 0. Okay, and clearly this is the total external force, this is the total external force, and this term is nothing but this is the reverse effective force, reverse effective force. Okay, and we say that from this relation, since the right side is 0, so we say that the total external force together with the reverse effective force in a system of particle always forms an equilibrium. Okay, and this is the mathematical proof of D'Alembert principle. Okay, so in the meantime we also prove an important theorem of rigid dynamics, which is D'Alembert principle. Okay, we already get here the statement and this is the proof. Okay, and this is our first answer of the problem, and this is the equation of motion of ith particle. Right, now we let that G be the center of mass, or it is known as also known as center of inertia or center of gravity. Same word, center of gravity, center of inertia and center of mass. And from the definition of center of mass, if we let the position vector of center of mass, this is generally taken as r bar. Okay, so here OG, this is r bar, and from the definition of center of mass, we write that capital M into r bar, this is equal to summation mi ri vector. Okay, mi ri vector, where where capital M be the total mass of the system. So capital M, this is equal to I equal to 1 to n mi. This is the total mass of the system. Now if we differentiate two times this relation, we say that m r bar double dot, okay, this is equal to summation m I r I vector double dot, right? Now this term is present in left side of the D'Alembert principle. Now we put the value of this is equal to summation I equal to 1 to n fi. Okay, so we put here summation I equal to 1 to n fi vector, and here we also may give a vector sign. This is arrow. M, capital M r bar vector double dot, this is equal to summation I equal to 1 to n fi vector, and we write this relation separately here. This is M into r bar vector double dot, this is equal to summation I equal to 1 to n fi vector. Okay, and this is nothing but the equation of motion of the center of mass, and this is the second answer. Find the motion of center of mass. Okay, and this is the motion of center of mass in vector form. Now our question is, what is the scalar form or what is the component form of this motion? If we take this point r bar, this is equal to x bar, y bar, z bar in 3 dimensions, and if we take the total external force as, this is summation fi vector. If we take fi vector like as summation xi I plus yi j plus zi k, okay, then we may write this equation into component form as, this is this is capital M into x bar double dot, this is equal to summation xi, capital M into y bar double dot, this is summation yi, and capital M into z bar double dot, this is summation zi, where summation xi is the external force along, or total external force along x-axis, this is total external force along y-axis, this is total external force along z-axis, and capital M be the total mass of the body. Okay, so these are the detailed explanation or detailed solution of our today's problem. Thank you for watching.